Right, so you want to learn how to differentiate basic functions to impress your friends. You find yourself drowning in complex terminology and strange symbols. Well, the title does not lie. The process is easy. Okay, let's take this simple quadratic function. If you're wondering what a function is, it essentially gives you an output for an input. For example, how much muscle you build is a function of how much you eat and how much you go to the gym, amongst other factors, of course. So, to differentiate this function, we follow a simple rule. Multiply the coefficient by the exponent, then subtract 1 from the exponent. Or, put more simply, times and take. To understand that, let's apply the rule to our function. First, we take 5x squared. Here, the coefficient is 5, the number next to x. The power, or exponent, is 2, since we have x squared. So, applying the rule, we times by the power. 2 times 5 is 10. Then we take 1 from the power. X to the power of 1 is just x. So we get 10x for the first term. For the second term, we do the same. Timesing by the power gives us 4, as 4 times 1, which is the power of x in this case, is just 4. Then, taking 1 from the power leaves us with x to the power of 0. Since we know any number to the power of 0 is 1, we can say that x to the power of 0 is 1, since no matter what number we put in as our x value, we'll get 1. So, for this term, we have 4 times 1, which is just 4. Finally, we have 7. It can be helpful to think of this term as 7x to the power of 0, since this would still just be equal to 7. Now, this makes it easier to apply the rule, and doing so, we multiply by the power to get, well, 0. So this term just becomes 0. As a rule, we know that the derivative of any number just becomes 0. So, altogether, the derivative of our function is 10x plus 4. And it's as easy as that. Ah, Jesus Christ. Okay. There's a little more to it than that. But for now, let's just get a better idea of what differentiation actually means. Now, you're probably thinking exactly what I was 3 years ago. What the hell are we doing here? Arbitrarily fiddling about with the numbers. What are we even looking at? Well, it's a good question. So, how do we interpret differentiation? Well, it's simple. Differentiation is the rate of change. Okay, now some of you might be thinking, how do we interpret that? Which is an equally valid question. Let's imagine, just for a second, that if you can, that you've purchased yourself a brand new car and you're looking to impress that girl or guy that you have been after. Naturally, in order to impress them, of course, you speed by as fast as you can. Brilliant. Right, let's graph out what just happened there. Okay, so first of all, let's take a look at the graph of the car's velocity against time. On the x-axis, we have time in seconds, and on the y-axis, we have velocity in meters per second. The car drove by, as we've seen, at a constant speed, meaning the velocity did not change, and therefore the rate of change of velocity was 0. Let's write a function to describe the car's velocity for the time that we could see it on the screen. Well, the function's going to be simple. V equals 2, because for any given time input, we get a velocity output of 2. Simple enough so far. So let's differentiate this function, v equals 2. Well, we know from earlier that the derivative of any number is 0. So the derivative of v equals 2, dv over dt, rather than dy over dx, since we have v on the y-axis and t on the x-axis, is 0. Well, okay, so the derivative of the car's velocity is 0. Well, what is the derivative of velocity? Since we know differentiating gives the rate of change, the derivative of velocity must be the rate of change of velocity, which intuitively we know is acceleration. As we just worked out, the derivative of the car's velocity is 0. Therefore, the car's acceleration is 0. This matches what we see on the graph. Okay, great. Well, hopefully you're starting to understand what differentiation actually is and its physical interpretation. If not, that's fine too. Let's take a look at this second graph and see if we can pull anything from it. This one's a little more complex. So, on the x-axis, we have time in seconds. And on the y-axis, we have how interested they were. Now, I couldn't find the units for this online, so I've taken it upon myself to label this unit interest points. So let's say, for the sake of argument, they have 2 interest points before they see you drive by. As soon as they spot you, they begin to lose interest at a constant rate. So let's write a function to describe how they lose interest as time changes. To write this function, we're going to need to use the equation of a straight line, which takes the form of y equals mx plus c, where m is the gradient and c is the y-axis intercept. We can see the intercept in this case is 2, and the gradient is -1, because for every 1 second, we drop by 1 interest point. So the function describing their interest over time is I equals -1t plus 2. Or, simplified, I equals -t plus 2, where I is interest and t is time. We know that differentiating this function gives di over dt equals -1. So, the rate of change of interest over time is -1, which we can see clearly on the graph. It's worth noting that, surprisingly, differentiation isn't used to model complex human emotions. In real life, you could perhaps expect to see it used modeling the height of a projectile over time, or maybe the speed of a car over time. Yeah, right. Well, if you like that, let me know. I've got a bit of time this summer, so maybe I'll make some more. Probably on differentiation, but you let me know. All right, cheers.